Happy Thursday, everybody. Welcome back to another wonderful day in Algebra 1. Hope you guys are having a wonderful day so far. Today we are talking about the zero product property. Before we get into that, a couple announcements. Again, homework collection 15 is due today. We had a quiz from yesterday. Hopefully you get that done. Chapter 8 test is coming up next week. So a lot of factoring stuff is going to be on that, just like we had in our quiz for yesterday. Graphing parabolas and quadratic functions will also be on there. And then last but not least, probably the biggest announcement of the bunch, if you're missing anything, those of you that are watching the video, all homework in all of the pages on It's Learning are going to be deactivated Thursday, May 27th at 3 p.m. So if you're missing homework, tests, quizzes, you got a little less than 2 weeks to get that stuff in. So get on it, get it done, and get your stuff turned in. Bump that grade up as high as we can as we make the push towards the end of the school year here. So we had homework from Tuesday, 8-1. If you want to check your solutions on that, check the filled-in notes on the page on It's Learning. Otherwise, we're going to jump right into some new stuff today. Again, talking 8-2, the zero product property. So we already know a lot of stuff about quadratic functions, and we have made several connections between the different representations on the quadratic web. So like between graphs and tables, table situations, equations and situations, and so on and so forth. As we did on Tuesday, talking about the catapults and shooting water balloons on a football field and all that kind of good stuff. So today we're going to develop a method to sketch a parabola from an equation without a table, using as little information as possible. We're trying to figure out how much information we really need, to graph a parabola. So 864, let's get to that first. So how many points do we need in order to sketch a parabola? 1, 10, 50. Think about this as we answer the questions below. So again, our sketches don't need to be exact. We just kind of want to get close. We want to get in the ballpark. We want to get near what it's supposed to look like. We don't necessarily need to be exact with our sketches. That's why it's called a sketch. It's not a portrait, it's a sketch. So can we sketch a parabola if we know only where the y-intercept is? So for example, we have a y-intercept with this graph. We know the parabola for part A is just at 0, -15. Can we sketch this parabola from just 1 point? I don't think so. That's a big old no. Absolutely not. No, we need more info. We need more info. We need like the x-intercepts. We would probably need a vertex would be nice. Whether it's going up or down would also make an impact. Again, if you look behind me on the whiteboard here, this is an example of a parabola going upwards. Again, we'll talk about how we get graphs like that a little bit more next week. But more information is what we need here. So if we go down and look at part B, if we know the two x-intercepts of the parabola, if we know where the x-intercepts are, like we have on the graph here, -3 and 5, is that still enough to predict the path of the parabola? And once again, I'm going to say no way. Because we, again, don't know if we're going upwards like the graph behind me or if it's going to be concave down like the catapult parabolas like we had on Tuesday. So again, we need more info. We need more info. So again, we could use either a y-intercept in this case or the vertex. One of those two things would be very, very helpful in figuring out what the shape of this graph would kind of look like. That's what part C is trying to tell us. So can we sketch a parabola if we know 3 points now? We know the two x-intercepts, -3, 0, 5, 0, and we know our y-intercept of -15. So it's these 3 points respectively. I think that would be enough to tell us what this graph is going to look like. Because we know from 0, or from, x is equal to 0 to x is equal to 3, this graph is going up just like that. We know that from somewhere down in here, we're going to be flipping back to go upwards. So at some point in this neighborhood, we're going to flip to go back up. And again, we know our direction is going up because our y-intercept is below our two x-intercepts. So because our y-intercept is way down here, the vertex is going to be somewhere down here as well. So we know that that graph is going up. So I think we need 3 things. We need the two x-intercepts, and we need the y-intercept, or we need the vertex. One of those two at the end. So in order to graph this, we need we need, for sure, the x-intercepts and either the y-intercept like we have here or the vertex of the parabola in order to get a rough estimate. So part D is asking, how do we find the line of symmetry? How do we find the line of symmetry between these two vertices, or basically what is the x-coordinate for our vertice here? And again, like we talked about on Tuesday, the line of symmetry is the halfway point between our two x-intercepts. So if we go halfway in between these two, what we can do to find that is take the difference of these two x-coordinates. So if we take 5 minus our second one minus -3 and divide that by 2, that's the halfway point between these two x-intercepts. So 5 minus -3 is, minus a negative turns positive, we have 8/2. So halfway between these 2 points is 4 spaces. So if we go from the left to the right, we go over 1, 2, 3, 4, and then we go from the right to the left, 1, 2, 3, 4. We end up at the same exact line, and our line of symmetry is the line that goes through x is equal to 1. So our vertex is going to be right there. So our line of symmetry, again, is x equals 1. Whenever we have a vertical line, the one thing that doesn't change is the x-coordinate. So it's x equals whatever number. The y's infinitely go up and down, unless our range restricts us at all. Perfect. Let's keep going. 65. So in problem 64, we learned that if we can find the intercepts from the parabola from the rule, that we can sketch the table or the graph without a table. So let's take a look at A here. What is true about the value for y of all x-intercepts? So again, if we're going through the x-axis, so if I draw a rough coordinate plane here, if we look at our x-intercepts, again, this is our x-axis, this is our y-axis. Whenever we have a point on the x-axis, like our x-intercepts, y is always equal to 0. Y is always, always, always equal to 0 when we have a point on the x-axis. So for this first part, again, value of all our y for our x-intercepts, y is equal to 0 for that first part. So what is true about the value of x for all of our y-intercepts? Again, when we have a point on the y-axis, let's say if this is our point down here on our y-intercept, y is going to be negative something. But we've been talking about this with our equations of lines for quite some time now. Whenever we have a y-intercept, our x value, x is always equal to 0 when we have a point on the y-axis. So y-axis, that means that x is equal to 0. X-axis means that y is equal to 0. So the intercepts on those corresponding graphs will always be equal to 0 for either x or y, depending on which one it's at. So again, if we're on the x-axis, y is 0. If we're on the y-axis, x is equal to 0. Again, that is what we're looking for there. So if x is equal to 0 for the y-intercepts, let's find what our y-intercept is going to be for this equation. So again, y equals 2x squared plus 5x minus 12. So if we want to find the y-intercept, we can just plug in 0 for x. So this equation becomes y equals 2 times 0 squared plus 5 times 0 minus 12. So anything times 0 is always 0. So these two terms are basically going to go away. 0 squared is 0, 2 times 0 is 0, 5 times 0 is 0. So we're left with y is equal to negative 12. So that means that our ordered pair, our y-intercept for our parabola here, x is equal to 0, y is equal to negative 12. And this is our y-intercept. So since our x-intercept occurs when y is equal to 0, write an equation that would help us, that we would need to solve in order to find the x-intercepts for the graph of y equals 2x squared plus 5x plus 12. So now when we want to know what x is when y is equal to 0, what we got to do is write an equation where basically y is equal to 0 and solve for x. So that equation would be 0 is equal to 2x squared plus 5x minus 12. So we would have to solve for x for both of these. We don't know how to do that yet, but we will very, very shortly. So in part D, the roots or the zeros of a quadratic expression are the values that make x, sorry, let me start over again. Choking on my words here at the end of the day. The roots or zeros of a quadratic expression are the values of x that make the value of the quadratic equal to 0. So again, whatever we plug in for x in this equation right here has to make the right-hand side equal to 0. An x-intercept is an example of a quadratic function, or the x-intercept of a quadratic function is a root. So at this point, like I mentioned before, we cannot solve this equation, but again, we will be very, very soon. We'll be able to solve that for x. So that'll be coming probably next week. So let's keep moving to number 66 at the bottom part of the page, zero product property. The equation we wrote in part C of problem 865 is called a quadratic equation. To solve it, we need to know, or we need to examine what we know about 0. So we're going to study the special properties of the number 0 below here. So Nathan, Sonia, and Gaston are playing a game where Nathan and Sonia each think of a number and then give Gaston a clue about their numbers. So using the clue, Gaston must tell them everything he knows about their number. So Nathan and Sonia's first clues is that when you multiply their numbers together, the result is 0. So I'm going to write an equation. I'm going to say that I'm going to call Nathan's number n. So let n equal Nathan's number. And I'm going to say s is equal to Sonia's number. So we know that n times s is equal to 0. So if we have these two numbers multiplied together and they equal 0, what conclusion can we make from that? So we know anything to any number times 0 is equal to 0. So that means if these two multiplies, or these two numbers, whatever n is, whatever s is, multiplied together to equal 0, one of those two numbers has to be a 0. So this, what Gaston can conclude is that either n or s has to be 0. Has to be equal to 0. Because in order to multiply something to 0, we have to be able to say that one of those numbers has to be equal to 0. So disappointed that Gaston came so close to figuring out their numbers, Nathan and Sonia invited Nadia over to make things a little bit harder. So Nathan, Sonia, and Nadia all think of secret numbers. This time Gaston is told that when their three secret numbers are multiplied together, the answer is still 0. So I'm going to add one more variable. These two, n and s, are going to stay the same. We'll say that a is Nadia's number this time, because we already have an n. So Nadia's number is going to be a. So for part B, we're saying that n times s times a is equal to 0. So if all three of those numbers multiplied together are equal to 0, that means at least one of them has to be a 0. At least one of them has to be a 0, because if we have a product of any combination of numbers together and they equal 0, one of them has to be 0. So n, s, or a, or more has to be equal to 0 for this problem. Has to be equal to 0. So again, like I kind of talked about already in part C, doesn't matter how many numbers are multiplied together. Absolutely not. So if the product of a number is 0, we know for sure that one of the numbers being multiplied has to be 0. And this is what's called the zero product property. So again, in general terms, if we have like a times b equals 0, that means that a or b will be equal to 0. And that is the zero product property. So again, whenever we multiply two numbers together, if the product of those two numbers is 0, one of those two numbers has to be 0. One or both has to be 0. Wonderful. Let's go to 67. So let's investigate how we can use this zero product property to help us solve the quadratic equation 2x squared plus 5x minus 12 equals 0. So examine the quadratic equation at the right. Is there a product that equals 0? So if we don't know, because we can't solve this, what I think we should do is let's maybe factor this and rewrite this as a product. So if we factor this, again, we're going to do, again, our diamond and our rectangle patterns here. So I'm going to put 2x squared here. We got negative 12. Negative 12. This is what the part that we're factoring, that green chunk at the top here. So the product of those two things together goes in the top of our diamond problem, which in this case is negative 24x squared. These two numbers are the same thing. Those missing boxes, those two things add together to be 5x. 5x. We need multiples of 24 that would potentially add to 5. So let's make a list of multiples. We've got 1 and 24, those don't add to 5. 2 and 12, those don't add to 5. 3 and 8, if we make one of those negative, they might actually add to 5. So let's plug those in. If I say 8x and 3x, again, we have a negative number up here. So when we multiply these two things together, one of them has to be negative. And if they add to 5, I'm thinking we got to make that 3 the negative one. So let's put 8x, negative 3. Now we can factor. So I'm going to say this is going to be 2x, this is going to be x, this is going to be 8, and this is going to be negative 3. So if we rewrite this as a product, now we've got x plus 8 times 2x minus 3 is equal to 0. So now that we have it written as a product, and the products equal 0. So basically, if we think about it as the zero product property from the last page, like again, A times B is equal to 0, that means that either A or B is equal to 0. So that means in this case, if we think of this as A and this as B, if these two things multiplied together equal 0, one of these two things has to be equal to 0. So since we know that one of these factors must be 0, we can set up two simpler equations to help solve for x. So we're going to use one factor at a time. Basically, we're going to take A, set it equal to 0, and then we're going to take B and set it equal to 0, and then solve for x. So we get two equations. So we get one down here for A, we'll get one over here for x, where we get, oops, I did this wrong. I made a little mistake here, everybody. I apologize for that. This should be a 4 instead of an 8. So before we go on, let's make this a 4 instead of an 8. So this is 4. This is also 4. Apologies for that. So now we can solve this. So x plus 4 is equal to 0. And also 2x minus 3 is equal to 0. Again, because when we multiply these two things together, they equal 0, so one of them has to be equal to 0. So whatever value we plug in for x has to make one of these two things equal to 0. So let's solve for x. In this case, on the left, we're subtracting 4 from both sides. So x on the left is equal to negative 4. On the right-hand side, we're going to add 3 to both sides. So we get 2x is equal to positive 3 divided by 2, x is equal to 2/3. Wonderful. So again, what do these two things represent? We have two solutions now for this quadratic expression, which started as 2x squared plus 5x minus 12. We factored that into x plus 4 times 2x minus 3. When we solved each of those two things for 0, we got two solutions for x. So what those two things tell us are the x values that make y 0. and where y is equal to 0 is our x-intercepts. So x equals -4 and x is equal to 2/3 are our x-intercepts for this parabola. Because again, that tells us where y is equal to 0. Again, tells us where y is equal to 0. Wonderful. So again, we know those 2 points are, or those 2 x values are our x-intercepts. We know our y-intercept. So if we plug in 0 for x, we can find our y-intercept. So we get 3 points in this case. Our y or x-intercepts -4, 0. We have 2/3, 0. And then our y-intercept when x is equal to 0 is y equals, when y is equal to 2 times 0 squared plus 5 times 0 squared, which we did on the last page. I'm just rewriting it as to show you how we get our y-intercept. And y is equal to -12, which tells us that our y-intercept is 0, -12, just like that. So now we got 3 points. We can graph this parabola from those 3 points, which I need to get my face out of the way so you can actually see the graph. So now we can plot those couple of points and see what this graph is actually going to look like. So first one, -4, 0 is right here. 2/3 0 is about right there. -12, if this was 15, this would be somewhere in this neighborhood. Might not be exactly right, but we can sketch the rough shape of this graph now. Let's slow down a little bit, and then we get up here, and our graph looks something like that for the shape of our parabola. Just a sketch, doesn't have to be perfect. So again, if we can factor our quadratic, and then we set each of those 2 sets of parentheses equal to 0, those tell us, or set each of those 2 things equal to 0, solve those 2 things for x, that tells us what our x-intercepts are, and then we can plug in 0 for x to find our y-intercept. So let's do one more. We're going to take a little bit different twist on this. I know we're getting a little bit long-winded on our video here. We'll try to go through it quick, but let's go to 68. So first things first, we want to find the x-intercepts of the parabola y equals x squared minus 2x minus 8. So again, let's do our diamond problem quick. We've got x squared, we've got minus 8. Those 2 things multiplied together are -8x squared. The middle, or the empty boxes here, add to minus 2x. So I think what we need to put here is going to be minus 4x and 2x. So this is minus 4x minus, or not minus, but this is going to be, let's fix that, 2x. So then when we factor this, we get x, we get 2, we get x minus 4. So our factored form is going to be x minus 4 times x plus 2 is equal to y. So again, our x-intercepts tell us where y is equal to 0. So again, x-intercepts, y is equal to 0. So if we take that y, turn it into a 0, basically we're plugging in 0 for y. We want to find the x values that make this thing equal 0. So we want to make 2 equations here where we set both of these 2 things equal to 0. So we've got x, let's try that again, x minus 4 equals to 0, and then we have x plus 2 equals 0. Now we can solve for x. So our x is equal to 4 on the left, x is equal to -2 on the right-hand side, and these are our 2 x-intercepts, again, at 4, 0, and at -2, 0. So let's plot those 2 points quick. So -2, 0 is right here, 4, 0 is right there. Those are our 2 x-intercepts that we just found by factoring and solving the 2 things equal to 0. And if we think about where the vertex is, remember, like we talked about, the vertex is halfway in between our intercepts, halfway in between our x-intercepts. So if we look, we've got 4 and -2, so the halfway point, 4 minus -2, all divided by 2 is equal to, again, negative minus negative is positive. This is 6/2. So this is 3 spaces on our graph to get to the middle point. So that means that this, x is equal to 1, is the halfway point, or the line of symmetry for our parabola, which is also the x-coordinate for our vertex. So if we want to find the y-coordinate for the vertex, we just got to plug 1 in up here. So y is equal to 1 squared minus 2 times 1 minus 8, and that'll give us our y-coordinate, which we can finally find the ordered pair for our vertex. So let's see here, 1 squared is 1, minus 2 minus 8, which is equal to y. So y, I think, is equal to -9. So our ordered pair for our vertex, 1, -9. This is the lowest point for that parabola, which 1, 2, 3, 4, 5, 6, 7, 8, 9 puts us right there. So the rough shape of this graph is just like that. So personally, which way is easier, using the vertex or the intercept? I personally like this method, using the vertex, because I think it gets us a little more accurate representation of our drawing, or about what our graph is supposed to look like. But again, it's personal preference. We get a rough idea either way using the y-intercept or the vertex. So hopefully that helps. Again, check the filled in notes for the homework answers from Tuesday. Other than that, again, zero product property is when 2 numbers are multiplied together and they equal 0, one of them has to be equal to 0. That's just mathematical fact there. 2 things multiplied together to be 0, one of them has to be 0. Other than that, homework for this evening, 822. Remember, homework collection this weekend. Start working on any missing work if you got any. Otherwise, have a great weekend, everybody, and we'll see you next week.